Next, let's discuss about induction. So what do you mean by induction? We know that whenever the magnetic flux associated with the coil changes, an EMF is induced in the coil, due to which a current is also induced in the coil. So this phenomenon itself is known as induction. To be more specific, it is electromagnetic induction. So the phenomenon of producing current in a coil due to change in magnetic field associated with the same coil or the neighboring coil is known as induction. And induction is a scalar quantity. Its unit is Henry or Weber per ampere. Two units are there for induction. Henry is the standard unit. Another unit is Weber per ampere. And there are two types of induction, self-induction and mutual induction. First, let's discuss about self-induction. So, in order to discuss about self-induction, consider a coil like this, which is connected to a battery and a key. Okay, when the key is closed, current starts to flow through this coil. So initially, when the circuit was switched off, no current was there. So no magnetic effect can be observed. Hence, initially the magnetic flux associated with the coil. And what is the symbol for magnetic flux? That is phi. So the magnetic flux associated with the coil was 0 initially in the absence of current. But as soon as the circuit is switched on, current starts to flow through the coil and the coil behaves like a magnet. So the magnetic flux will be associated with this coil. So when the circuit was switched on, some amount of magnetic flux is associated with the coil. So the magnetic flux increases. Initially it was 0, and when the circuit was switched on, some magnetic flux began to accumulate or began to associate with this coil. So the magnetic flux increases from 0 to a certain value. There is a change in the magnetic flux, and you know, whenever there is a change in magnetic flux, an EMF is induced in the coil, and this EMF always opposes its cause. As per Lenz's law, this EMF always tries to oppose its cause. That means it always tries to oppose the growth of current or the flow of current through the coil, because the flow of current through the coil is responsible for that induced EMF, and that induced EMF always tries to oppose its cause. That means this induced EMF always tries to oppose the growth of current through the coil. So here a current is induced in this coil due to the change in magnetic field associated with the same coil itself. So this type of induction is known as self-induction. The phenomenon of inducing current in a coil due to the change in magnetic flux associated with the same coil is known as self-induction. So here what will be the total magnetic flux associated with the coil? You know, flux is denoted by phi. So what will be the total magnetic flux? In order to calculate the total magnetic flux, you should consider the number of turns of the coil. Suppose the coil has n number of turns. So the total magnetic flux associated with the coil will be n phi, because phi is the magnetic field associated with a single turn. So if there are n turns in a coil, then the total flux associated with the coil is n phi. And we can write this total magnetic flux is directly proportional to the current I. Why? Because as the magnitude of current flowing through the coil increases, the magnetic flux associated with the coil also increases. When current increases, more and more magnetic flux gets linked with this coil. So the total magnetic flux is directly proportional to the current I. And this proportionality symbol can be removed by adding a constant. The constant that we are adding here is capital L into I. This constant L is known as self-inductance. It's a very important term. Self-inductance. Okay. So the constant L is self-inductance. And how will you define self-inductance? here from this expression, what is L? L is equal to N phi divided by I. So from this expression we can easily define self-inductance L. What is self-inductance L? It is the ratio of total magnetic flux to the current flowing through the coil. Okay, so self-inductance L is the ratio of total magnetic flux to the current flowing through the coil. So since we have got an expression for self-inductance and magnetic flux, now we can derive an expression for induced EMF in the coil. Because an EMF is induced in the coil due to which a current is induced here. So what is the expression for that induced EMF? And you know, as per Lenz's law and Faraday's law, induced EMF E is equal to minus d phi by dt. Here we need to consider the number of turns 2. So here we can modify this equation as minus d by dt of n phi. Okay, that will be the total flux. Now substitute the expression for n phi. See, let this be our equation number 1. As per equation number 1, what is n phi? N phi is Li. So therefore induced EMF E is equal to minus d by dt of Li. And you know L is a constant. So you can take it outside the differential operator. So it will be equal to minus L into di by dt. So what is the expression for induced EMF? Induced EMF E equal to minus L into di by dt. And this is our self-induced EMF. So what is the expression for self-induced EMF? Self-induced EMF E is equal to minus L into di by dt. And the negative sign here indicates that induced EMF E always opposes the growth of current di by dt. Okay. And what is the unit? Unit is Henry or Weber per ampere. Henry or Weber, WB, Weber per ampere. Okay, that is the SI unit of self-induction. And what is the expression for self-induction? Induced EMF. Sorry, what is the expression for self-induced EMF E? It is minus L into di by dt, where L is the self-inductance. And you should remember the expression for self-inductance. Okay. So that's all about self-induction. Next, let's discuss about the expression for the self-inductance of a long solenoid. So for that, consider a long solenoid like this. Let L be the length of the solenoid. And what is the expression for magnetic field in the solenoid? We had studied in our previous chapters. That means the magnetic field inside the solenoid is mu 0 n I, where mu 0 is the permeability of free space and small n is the number of turns per unit length of the solenoid, and I is the current flowing through the solenoid. Now here let capital N be the total number of turns, then small n is equal to capital N divided by L. That means total number of turns per unit length of the solenoid. So here we can write B is equal to mu 0 into, instead of small n, capital N by L into I. Now, what is the expression for magnetic flux phi? We know magnetic flux phi is equal to B dot A, that is BA. Now, here the theta is 0, so B dot A can be considered as BA cos 0, that is BA. And if you consider the total number of turns, here the magnetic flux can be written as phi is equal to BA into N. That means we should consider the number of turns too. Okay. So here total flux phi is equal to BAN. Now substitute the expression for B. So as per this equation, equation number 1, B is equal to mu 0 n by L into I. So substitute mu 0 n by L into I, then into A into n equal to mu 0 into n into n, that is n square I into A by L. Okay, so this is the expression for total flux, mu 0 n square IA by L. Now let this be our equation number 2. Okay, also we had studied the total flux phi is equal to L into I. So let this be our equation number 3. We had studied this expression in the previous slide. So the LHS of equations 2 and equations 3 are same. So we can equate the RHS part. Whenever you get the RHS part, you will get Li is equal to, what is the RHS part of equation number 2? Mu 0 n square Ia by L. Now here we have I, here we have I. So like terms are cancelled. Then what is left? We are left with L is equal to mu 0 n square A by L. Okay, so this is the expression for self-inductance of a long solenoid. Self-inductance L is equal to mu 0 n square A by L, where mu 0 is the permeability of free space, n square, n is the total number of turns, A is the area of the solenoid, and L is the length of the solenoid. Okay, and we can again rearrange this expression. So we got self-inductance of a solenoid L is equal to mu 0 n square, so mu 0 n square A by L. Okay, so here suppose the solenoid is not present in a air, some medium is present in the solenoid. Now here suppose the solenoid is introduced in some other medium other than air. So what will be the expression for self-inductance? Then self-inductance L will be equal to mu into n square A by L, because we know that mu naught is the permeability of free space, and we can use this expression only if the medium is air or vacuum. And if solenoid is introduced in any medium other than air, we should substitute mu instead of mu naught. Mu represents permeability of that particular medium. And we had also studied that mu is equal to mu naught into mu r, where mu naught is the permeability of free space and mu r is the relative permeability. So here instead of mu, substitute mu naught into mu r into n square A by L. So this is the expression for self-inductance of a solenoid. So two expressions are there. You should remember both the expressions. First expression is the self-inductance of a solenoid when it is kept in air, and second expression gives the self-inductance of a long solenoid when it is introduced in a medium. So from this expression it's very clear the self-inductance of a solenoid depends upon some factors. Which are those factors? N, that is number of turns, then area of the solenoid, and also the permeability of the medium. Okay, so these are the factors on which self-inductance of a solenoid depends upon: number of turns, area, and also the permeability of the medium. Next we can discuss about back EMF. So what do you mean by back EMF? This self-induced EMF is also known as back EMF because it opposes the growth of current. So this back EMF is not a new concept. Our self-induced EMF itself is the back EMF. Why do we call this as our back EMF? Because the self-induced EMF always tries to oppose the growth of current. Hence, we can call our self-induced EMF as back EMF. Okay. Current needs to do some work against this back EMF because self-induced EMF or back EMF always opposes the growth of current. So, if current wants to grow in the circuit of, or if more and more current is to be, if more and more current wants to flow through the circuit, current needs to do some work against this back EMF. And this work done is stored as magnetic potential energy. When current increases in the circuit, magnetic flux in the circuit or magnetic flux associated with the coil also increases. That means there is a change in the magnetic flux due to which an EMF is induced, and this EMF opposes the growth of the current. And some work has to be done by the current against this self-induced EMF or back EMF, and this work done is stored as magnetic potential energy. So let's find out an expression for this work done. We know that the power associated with any circuit, electrical circuit, power P is equal to potential difference into I. Power P is equal to VI. We know that what is this power P? Power is nothing but dW by dt. That is the expression for power, rate of work done. That is power. You had studied this concept in your plus 1 physics, also in class 9 physics. Power is work divided by time equal to potential difference. Here instead of potential difference, in this case we will think about EMF. And which is our EMF? Our back EMF epsilon into I. And also in the previous slide we had discussed what is the expression for the self-induced EMF. It is minus L into di by dt, but here for our convenience we neglect that negative sign. We just consider the magnitude. So the induced EMF or the back EMF is L into di by dt. So here instead of E, substitute L into di by dt into I. Okay. So we got dW by dt equal to L into di by dt. Here just omit this dt and dt on both sides. So you will get dW is equal to L I into di. dW equal to L I into di. Now we need to find out the total work done. So in order to find out the total work done, just integrate this expression. And when you integrate dW, you will get W equal to L is a constant. Take it outside the integral. Then you will get L into integral I di. Integral x dx is x square by 2. So integral I di will be I square by 2. That is equal to half L I square. So this is the expression for total work done by the current against this back EMF or induced EMF. So this is the expression for magnetic energy 2, potential energy 2, because this work done itself is stored as magnetic potential energy. So this expression itself will be the expression for magnetic potential energy. What is that? Half Li square, where L is the self-inductance and I is the current flowing through the circuit. So half Li square is the expression for expression for work done by this current against this induced EMF or back EMF, and this itself will be the expression for the magnetic potential energy. So that's all for today's session. With this, I am concluding my session. Notes of the topic and YouTube video have been uploaded. Just go through it. Also, learn the notes very well and attend the test seriously. We will meet in the next session. Till then, take care. Stay home, stay safe. Keep learning, all of you. Thank you.